I'm just going to give us a talk about amateur spectroscopy for everybody. And you were a last minute talk. I mean, you actually came in, we actually had all our slots filled, and I thought this was such a neat topic that I said, you know what, go ahead, come down, we'll start an hour early. And I'm glad to see that we have a good amount of people here to view his talk. This is something of interest to me. I think this is actually a very neat topic, very, very interesting to do. I personally like to do this myself. I'm going to eventually buy Tom software and refraction grading and do some spectroscopy on some stars. And I believe you showed me you can do it on galaxies as well. You actually measured redshift, back calculated how fast galaxy was moving away from us. So I thought this was very interesting. I know that Mike Mooney, one of our club members, was very interested in this talk, but he's unfortunately downstairs. So, Mike. So Tom is gonna, let's see if I could steal from his quote. In a way, he's gonna light a fire under your butts. Take it away, Tom.
Thanks a lot. You know, my wife says I'm supposed to dress for success since it's a spectroscopy talk. You see the infrared and the ultraviolet over here. I don't think she'd like it because it doesn't go with the shirt. I think that's the problem. Thanks a lot. It's really great to be here. It's my first time at the Winter Star Party, and it's just a fantastic group, as you all know. I'm just delighted to be here. I'm going to go very fast. I'll try and stay out of your way so that you can see the screen, so I'll bounce around a lot. This show has some components from a gentleman named Robin Leadbeater. I'll be talking about him a little bit. He's one of the pioneers in this field. So how is it that we've managed to discover so much about the universe when we've barely set foot outside our own front door? Now, you know, you can take static images, and we do a lot of this here. Static images, this is a Hubble deep field, and see two dimensions. Now, some of you may know this. In fact, there's a lot of you here who know a lot more about some of these topics than I do. But if you don't know this, I find it remarkable that the field of view of this shot is the size of a tennis ball at 100 yards. So walk 100 yards away, and that's how much of the sky you're looking at. There's a lot out there if you look deep enough. So we can also get free Wi-Fi if we want. So we can see two dimensions, and we can even see fleeting three dimensions. This is a cool slide. This is Astronomy Picture of the day, and if you look carefully, you can actually see these stars going on and off. These are our Lyrae stars, standard candles. This is over the period of just one night. I didn't really have a sense for how long it would take for these to go on and off. So again, that's sort of a fourth dimension. And then if we spread the colors out, we can get a fifth dimension. And that's what we're going to talk about today. And I'll be showing you some of these over at my table in Vendor's Row a little bit later today. I have some things set up that will actually show spectra of this sort. Again, it's sort of a barcode that we've learned to discern. And, you know, I was reviewing my slides last night, and I'm happy to say that I still felt that sense of wonder that I'd like to communicate as to what this magnificent accomplishment as humans we've made over the last 200 years. And we'll look a little bit at the history and the science, and then we'll look at the kinds of things that we can do. But it's marvelous because 200, 300, 400 years ago, we didn't know any of this. And over generation after generation, standing on the shoulders of previous giants, we've learned more and more about how to discern starlight. So here, for example, and I'll show you this in a little scope in front of my table, magnesium triplet, sodium doublet, and we'll look at what those are. Now, just to look a little bit at the history, we'll jump around a little bit. I'll get the history and science out of the way as quickly as I can because I know we're all hands-on types of people. Wollaston in 1802 observed some spectral features, and Fraunhofer, whose name you may have heard, is the first person considered the father of spectroscopy who developed a diffraction grating, which is like a prism. So this dovetails well with the previous discussion that we were hearing from Bob about rainbows. This is Fraunhofer. I love the way these guys are all dressed. Look at the boots, and they're real dandies. They don't know what they're looking at. They're looking at pretty colors in a rainbow with gaps, with holes in the spectrum. They don't yet understand what it is, but it's a natural curiosity. And at this point during, well, let's just keep going. Again, I love this slide. We've all seen spectrum slides over the years. The wavelength spectrums, we're just looking in the visible lengths, visible wavelengths here. We're not looking in the infrared or the ultraviolet. Just wanted to clarify what we're looking at. Now, this is just a very short side trip. I didn't get to bring a prism. I wanted to set a prism up in the booth and have people, especially the kids, point out how far into the ultraviolet they could see. Because as we age, we can see less and less deep. And I know there's some people in here who can identify with me. I just had cataract surgery. They replaced my lens. I was hoping to see deeper into the ultraviolet, but when they gave me the little card for the lens that they replaced in my eyes, it said, hey, we've got an ultraviolet filter in these to protect your eyes. So I didn't get any additional depth, darn. But there are some remarkable things that you can see as you go deeper into the ultraviolet.
You don't have to worry about any more cataracts.
That's true. So, again, a little bit of the history. Sir Isaac Newton with a prism, which you just saw in the last hour, something about raindrops, anything that is finely lined like a CD. You can even make a sun spectroscope with a CD or DVD. Don't look directly at the sun. Don't look at the sun in a reflection on a CD either. I've never been able to make those CDs work because I'm always afraid of blinding myself. Now, this is a book by Sir Isaac Newton. And again, it's the first edition from 1704. This is in the Sunday New York Times Magazine. They're selling it for only $75,000. I know that the Winter Star Party budget has been a little tight, but I was just thinking, maybe as a gift, an honorarium for my talk, for my library year. Actually, I went out and I bought one on Google for $3. So Gutenberg works. You can buy books much less than what the original copies cost. But let's go back even a little further in time. Let's go back 500 million years. This is a fossil that was discovered from that era. And Professor Andrew Parker looked at that and said, hey, that looks like a CD. That looks like a reflection grating. And if it's a grating and it's reflecting, then maybe the critter that left that behind looks something like that. So whether it's peacocks today or certain butterflies, nature also has a way of creating gratings naturally that will create rainbows. Now, one interesting thing about this particular era, 500 million years ago, there was a huge explosion in the variety of life forms on the Earth. And Professor Parker says he thinks that, again, there's no reason for diversity visually until you have eyes. So he thinks that they co-evolved. As eyes evolved, this kind of diverse appearance evolved. It's not exactly astronomy, but it does relate to our topic. So we fast forward to the middle of the 1800s. Some of you know, many of us know about Bunsen and his Bunsen burner. What Bunsen invented his burner for, and frankly, he didn't patent it. He left it open source, which was rather novel in that day and age. They were burning everything they could find and going through a prism and then looking at the resultant spectrum. They still didn't understand what they were looking at, but they wanted to study everything they had to gather data so they could begin to interpret it. Kirchhoff was also working with him and also a theoretician. Very briefly, when you put starlight through a cloud, a cool gas cloud around a star, you can get two types of spectra. One is an emission spectra where you have very bright lines, and this is an absorption spectra where you have gaps. This is what they were observing back at the turn of the 1800s. They didn't understand what it was. So elements have fingerprints, so you can see hydrogen's bands are very different than helium's bands. And those help us identify what's on stars. About 80% of the research that's done today in astrophysics is done using what we're going to talk about in the next few minutes. In about 1835, and I'm jumping around a little bit in time here, this guy August Comte said, we'll never be able to learn anything about the stars. They're too dang far away. Well, he was dead wrong. Really, 20 years later, 30 years later, they were doing all sorts of spectroscopic research. Maybe he was wrong. He's a French philosopher, so go figure. Maybe that contributes to his being wrong. But how do we get these absorption and emission lines? How do we get these characteristic fingerprints that help us identify the composition and other physical properties of stars, which we'll be looking at examples of as soon as we're past all this history and science stuff. Now again, I apologize, some of you know all the subject matter, maybe not the history, but the science, but I want to get everybody at least up to the same level. Niels Bohr, around the turn of the 1900s, he had a model of the atom which had electron shells, which were numbered, as we see here, and there are electrons in the shells, and when they jump to a different shell, they give off energy, which shows up as a line in a spectrum. A jump between other shells, this is between shell 3 and 2 rather than 5 and 2, gives a different color. And finally, this jump here. Now the reason I did this 1/3 instead of working down sequentially is because you're going to get sick and tired of this number 4861 over the next 20 minutes. This is a very well-known hydrogen absorption or emission line. It's really great because it's like a beacon that we can use. Those of you who have been by the table have seen me running the software using that line to do calibrations. So what amazed me last night when I was thinking about this that I mentioned earlier is that we're able to plumb the depths of atoms by looking at a macro scale light band. We're looking down in and we understand, although this is just one particular model, not the quantum model, we understand what's going on internally and can use this to do science. It's just stunning to me that we have been able to deduce these models. Now here's Einstein chilling with Niels Bohr a little later in his life. Some example spectrographs here. These are at OHP in France. This is where the first exoplanet, Pegasus 51, was discovered. I had the opportunity to go there a couple years ago. By the way, we have 2 spectroscopers here. I don't know if they're here. Jim Edlin's here and Torsten's here. The 2 of them are here, and they're actually doing spectroscopy in the evenings here, so you can check out their gear. This is in Chile, and it just looks like a big instrument until you spot these people, and then you realize it's a really big instrument. It's enormous, really. So I hope I'm not making you dizzy going back and forth like this. So here is, this is the beer cooler on the Hubble, or so some would say. This is the Hubble Spectrograph that so much valuable research has been done on. And finally, we get into amateur gear. Now this is Dale Mace's. I called him. All these images are used with the permission of their owners. And I said, Dale, what is that? It looks like you just took a fluorescent tube and just stuffed it into your gear. You can even see the little pins on the ends. Well, it is. It's an argon thorium tube that he uses for calibrating. But it doesn't have to be that complicated or expensive. It can actually be very simple. And this is what I'm showing at the booth, is this grating right here, which is called a star analyzer grating. It's a diffraction grating. It has very, very fine lines, just like a DVD, 100 lines per millimeter, if you can picture that, 100 lines fitting into a millimeter. And it's very inexpensive. And again, my mission, although that's a loaded word, I sometimes call myself an evangelist for spectroscopy. That's also a loaded word. But the excitement for me about spectroscopy is how inexpensive and easy it is to do things. And really, my article in the Sky and Telescope magazine last August helped dispel this ignorance that, well, gee, spectroscopy is really only going to be for people who are more advanced than I am or have more money than I do. Here's a really simple way to do spectroscopy. You could do this with a grating today with a DSLR and a zoom lens. Very simply, there's our star analyzer right on the nose. Notice there's no tracking. If you orient the grating so that the star moves vertically across the dispersion of your spectrum, you get a smear. We don't mind that. We're going to be summing up all the pixels in these columns anyway. So you don't even need to track in order to do spectroscopy. Now that's only on bright stars. You know, my background, just to step back a bit, is I've been doing astronomy for 20-some years. I've done some imaging, but imaging wasn't really capturing my attention the way it does some people. Some of the challenge was that I'm from Seattle, so it was tough to do imaging anyway. But also, again, I just found that my interest was leveling off, excuse me. And I wanted to do some science. So I picked up this grating, and that's what got me launched into this. These gratings have been around for 5 or 10 years. We're going to look at some other examples of things that you can do with gratings. First of all, how to mount them. This is probably the first way that they were used. This is just a, 2-cam, 2U-cam. Anybody who uses a hose clamp on their astronomical gear is okay with me. And we'll have other examples of that coming up. Here's a imaging source video camera. You can do it with video. You've seen that maybe at my table down in Vendor's Row. You can mount one of these gratings in your filter wheel. Or you can also, in that picture in the lower left-hand corner, shows this on your camera lens, right on your DSLR, and we saw this a minute ago in another slide. You can just screw on an adapter like this, and then screw the grating on here. So there's lots of different, or just screw it right into the nose piece of your FITS camera. Doesn't have to be video, doesn't have to be color. Here's a higher resolution spectrograph. This is a do-it-yourself kit for about $800. Most people start with a grating and get their feet wet that way. Here's an even more expensive device, and we'll look at some examples of the kinds of things that we can get from that kind of device in the next few minutes. So, but even when you're doing the high resolution stuff down here, you can do the keep it simple spectroscopy up here. There's the grating up there right on the nose piece of the DSLR. Okay, we're done with all that. History, theory, equipment. We did a big race through on that. Let's see what we can actually do. Again, to review what we're doing, let's just bring this whole slide up so my knees don't give out before the end of the talk. We have the star here. We put the grating here. And we have the spectrum, the rainbow, just like it was coming off of a raindrop. The light's getting smeared out into a spectrum. This is our sensor on our camera. Now, the one little bit of technical issue when setting this up is if our sensor was way out here, this rainbow would continue to spread, be perhaps too dim, but might even fall off of our sensor. So when we have the grating in our telescope, not on the front of the camera, this distance here needs to be approximately right. It's not like a focus that has to be right on, but there's ways to figure out what that distance is. It's 30 to 100 millimeters or so. But so let's look at an example of that. Yeah, sure.
Focus on the grating, or you focus past the grating to
You focus on the star or the spectrum itself. Good question. You can't really see the grating. Now, what we're doing is a great question. It reminds me I wanted to mention. This is slitless. On more sophisticated equipment, and we'll look at examples of that in a moment, you actually have a small slit which gives you much more resolution. And we'll look at how that works in a second. It's such a pleasure to see this in the dark room. I don't know how many of you came by my sun-drenched table out in Vendor's Row. Whether it's these slides or my software, I hate to see them all just totally bleached out by the sunlight. This is a pretty image. I think this was in the article in Sky and Telescope in August. These are the stars in Oh Be a Fine Girl, Kiss Me order. Hot stars here, cool stars here. A couple of interesting things to look at. This is that hydrogen bomber, that 4861 number that I mentioned. Very prominent hydrogen beta line. Notice that it's brighter here, or darker, stronger here than above or below. It's a Goldilocks type situation. These hot stars are too hot, and so the absorption is less because the electrons are just jumping right past the shell that makes this for transitions. And down here, the stars are too cool. For those of you, again, who aren't familiar with the Oh Be a Fine Girl, Kiss Me, these are hot, and then this is just the sequence. It's an acronym, mnemonic to remember the order, which is a totally nonsensical order that's based on history of how we label stars at different temperature. Down here are the cool stars. Now, this is done, by the way, with our grating and with an imaging source video camera and a 20-centimeter telescope. So down here on the cool stars, look at all these absorption bands down here. This is because these stars are cool enough to support complex molecules. Up here, they just get broken apart if they form. Down here, they can exist for a period of time and actually absorb light. Qualitative spectroscopy, it's very pretty. It confirms what we've all read. And that's going to be a theme I'm going to return to several times, and that is what this did for me, what spectroscopy did for me is made what I'd read over the years more real. I had probably seen charts like this, but when you actually touch the data, then it becomes yours. And doing this kind of thing, there's no quantitative here. This is just pretty. But there's still something to be learned from it. And again, this edifice of human knowledge I talked about earlier that we've evolved over the last several hundred years, this is one of them, that we know how to classify stars by the absorption lines that we're seeing from great distances. So if we want to talk about that little gap there, you may or may not be able to see in the crosshairs, rather than just saying, gee, there's a little gap there, we can plot the intensity. So here what we've got is the starlight coming through the grating, and some of the light just goes straight through and becomes the star. As we sum up and plot the intensities of each column here, that peak is the star peak, and this represents this rainbow, which could be on a black and white camera or a color camera. So that dip right there is that barely discernible dip in the actual spectrum. This is called a spectrum. This can be called a profile or a graph. Once we get to this point, we're ready to do science. I wanted to do science with my telescope. I liked and I admire the kinds of imaging that's being done. You know, we're not all going to be Don Parkers or Ted Wolfs. Some of us don't have the equipment, skill, time, or interest in doing that kind of thing. But I'm glad those people do what they do because it's just gorgeous stuff and it helps capture our imagination. This complements that because it helps us understand what we're seeing. Let's look at some examples. Again, this is my software. I'm not going to spend much time showing my software here. This isn't a software demo. But over here is a star, and there's the spectrum. And I'll flip to it just for a second and spend about a minute or two just to give you a sense for what goes on. So I'm playing a video here. This was a video made in Seattle with a C8. It's playing at 5 frames per second. Right now it's just noise over here. There's the star and the spectrum, and actually the way it came in, I didn't set it up that way, but I had my grating screwed on so it was cast across the diagonal of my sensor so it would fit on. But the first thing I can do is just rotate it around so it's horizontal so I can study it. Something you don't want to do in more advanced imaging because it can introduce artifacts. And then I can just grab these capture boxes and drag them around the area I want to study. So now, in real time, the software is doing what I showed you on the previous slide or two, summing up each column. So that peak there is the star, and this corresponds to the starlight being spread out into a spectrum. This is a black and white camera, so we don't see the colors, the Roy G. Biv red, orange, yellow colors here, but on a color camera you would. So this is bouncing around because we're playing it at 5 frames per second. Now, we all know that atmospheric seeing changes what we see when we're imaging, and that we can stack images to eliminate some of that noise. It's fun for me to see that happen real time. The software has built into it some real-time averaging, which when I turn on here, watch how this stabilizes nicely. There we go. It's just settled down. We're averaging about 100 frames in real time here. So that little dip right there that comes and goes is that there. So we're now doing science, and without spending much more time at this, we can calibrate it in angstroms, and we can see that absorption line in the synthesized spectrum is helping us to identify what that is. Final step, and then we'll go back to the PowerPoint, is, okay, we've calibrated this in angstroms, which is a measure of wavelength. How do we know we did it right? We've got angstroms, we've got a pretty rainbow, but does it correspond to what others have done before us? Well, one thing that we can do in the software is we can say, show us what the hydrogen bomber lines would look like on this image. So here we can see these lines correspond to the hydrogen bomber wavelengths, and you can see they go through a variety of the features here. So we've done our calibration properly. Now this is vague on a C8. It's the first time I went out with a grating, many years ago, came in with grass-stained blue jeans, and sat down the next morning to try and process my data like many of us do. My experience was with the software that was out there, I couldn't get it to work right, and I figured, well, I'd better write my own. I wrote this pretty much for my own use, but then it got out of hand, so says my wife, and it gave me an excuse to come to the Winter Star Party, so I'm happy about that. So let's look at some other cool examples. This is done with a Canon DSLR, 30-second exposure. That's one of the things I'm going to be harping on, is that this isn't hour-long integrations. Now, you can do hour-long integrations to dig deeper, but you can get very interesting results right out of the gate. This is a DSLR on a mechanical astrotrack. There's no guiding or anything going on. Wolfrey A star, these are very old stars. There's some of you here who can help explain what they are better than I can. They are hot stars with a cloud or shell of carbon around them, and that shell is glowing. So we are seeing emission spectra off of those. Now, for those of you who are even more technically oriented, normally we wouldn't be able to see these. They'd be too narrow. But because that shell is expanding so quickly, there's what's called Doppler Broadening. So we're actually able to see them with a $179 grating and a webcam. Pretty amazing. But now that you've seen that, before I go on to the next slide, you might think, Well, that's sort of cool. That's an emission spectra. Let's do something else that has an emission spectra. Let's do M57. So let's take a look. Well, that's not exactly what we've been seeing up until now. We can actually see the donut in every wavelength that's being emitted. This is a difference between a slitless grating and a much more expensive and difficult to use slitted device, which we'll look at some examples of in a few minutes. We can see our ionized oxygen and our hydrogen beta here. But again, it'd be a little tough to do science here. I mean, where is this line? Is it there? Is it there? How would you figure out how to graph this if you wanted to have a peak associated with each of those? So here is an example done with a higher end spectrograph of M42. Now, frequently in talks like this, I'll ask the group, how many of you have imaged M42 2 dozen times? And most hands will go up, especially I would think in this group. So there's a hand. So this is a point where, for me, I just wasn't getting enough thrill out of re-imaging objects that I'd imaged before. So this is done on a slitted spectrograph, and the interesting thing about this is you can see these two peaks. There's the hydrogen alpha, there's the ionized oxygen. Couple interesting things. Look how there's no data in here. There's nothing going on. That's why urban light pollution filters work so well, is because we can knock out all the light, the street lights that would be showing up in this area with no loss on our real data. It's also a good indication, this, as to how we can do amateur spectroscopy as astronomers in our homes or in our suburban locations. The noise floor here is very low. But imagine it was up here. We'd still see some interesting peaks. So one of the reasons more amateurs are doing this kind of thing is because it can be done from urban locations without a lot of consideration as to urban light pollution. Some of the best spectroscopy in the world goes on in France. Christian Buil, some of you may know his name, B-U-I-L. He pioneered CCDs in the 90s. He's now a spectroscopist. That's why I went over to France 2 years ago to meet him and some of the other people who are in that community. It's really a remarkably neat community of people doing pioneering work. Here's a fun one. This is Uranus and Neptune. This is done with one of those imaging source video cameras in the same telescope we talked about a moment ago. This is done by Torsten Hansen out of Germany. And you'll see here, there's the absorption bands. And when we plot them, we see very deep dips on Uranus and Neptune. These are the methane absorption bands. Who would have thought we'd be able to do what scientists 50 years ago were having trouble doing, and that is detect the atmosphere of a nearby planet. These are point sources, which is why we can look at them with a grating like this one. Now, this is a quick article that is basically saying that Draper imaged a comet. Now, the Draper catalog, many of you may know, wasn't actually created by him. He had passed away. His wife funded the catalog. And we're going to look at an example of a spectrum done with a star analyzer on the nose of a camera. There's the comet. And here we can see some of the complex molecules thought by most to be the building blocks of life, the complex molecules that were the precursors to life here on Earth. So again, just the kind of thing that can be done. Now, I mentioned earlier that hose clamp. How about this? Anybody who uses a C-clamp on their rig is okay with me. You know, it's a great setup. There's his video camera. This is done by Robin Leadbeater, who's the designer of the star analyzer. There's the star analyzer itself. This is a meteor traveling in the up direction. There was a bolide right there. We can see some of the minerals that we were able to detect. When I talked to Dennis DeCicco at Sky and Telescope about 3 years ago about this software, you know, I was just saying, you know, I'm thinking of writing it. What do you think? He's a big spectroscopy enthusiast. He said, Tom, spectroscopy is a niche in a niche. You know, it's not a big market. At that point, you know, I didn't care. I was having fun, as I still am. If spectroscopy in general is a niche in a niche, meteor spectroscopy is like a black hole in a niche in a niche. You know? There aren't a lot of guys or women doing this kind of thing. It's tough to do. In fact, I was going to do an advertisement at the end. I'll do it right now. I give the same talk to clubs over the web via webinar format, where there's a little live video window up here. So if your club you think would be interested in this kind of thing, it's new, it's novel. I've done several dozen clubs. It's for free, and it's remarkably effective. I've done some very big clubs, and I can talk to you about it later. And whatever the connection was to that, I lost. So let's just keep going. You know that happens, doesn't it? So this is a cool video that I'll play twice because it's very fast. It's a solar eclipse. Let's take a look at it. It's overexposed, There's the sun. There's the spectrum coming in off a video camera with a star analyzer on it. Let me just play it again now that you know what you're looking for. You can watch that spectrum pop in. Short and sweet. And you can see those little disks there. Let's go to the next slide where we can actually see a little bit more of the detail. So there's the sun.